All right. Starting off with TESS. So TESS is Transiting Exoplanet Service Satellite, which is what I'll be talking about, and how this session will go about is we'll just first of all know what TESS is, how it functions, who built TESS, right, and what's its goal, right? What is it supposed to do? Which is most of it is in the in its name itself. Other than that, right, I'm Chetan Chawla. I already gave you a session, so I hope you guys know me by now. I'm a tech consultant right now, and I used to be an astrophysics researcher at ASIAA Taiwan, where I was working on TESS itself. So I'll be talking about the same. All right, so TESS is the Transiting Exoplanet Service Satellite, as I said, and it is built by NASA, as you can see on the top here, right? It's a great satellite. It really worked so well for the last couple of years. It was launched in 2018, and it's a planet hunter satellite. So it is looking for planets, in the stars that are other than our sun, and it's an all sky survey monitoring satellite. So basically it covers the whole area in sky, and not just look at one particular region. And it is it was supposed to be looking for over 200,000 bright stars for finding those planetary transits. And most of you must have attended that lecture where we talked a bit about the exoplanet detection method. Transit method was one of those. We'll also discuss the same in a bit more detail going forward. But TESS is supposed to look for these planetary flux dips or the brightness dips to look for transits. It has four 2K into 2K resolution cameras, as you can see in the picture on the right. And each of these covers, so basically there is a 96 by 24 degree strip in the sky, which is being covered at visible wavelengths, so 600 to 1000 nanometer wavelengths, which is basically almost around the wavelengths that we see everything at. And these individual strips in sky that it looks at one time is called a sector, and then it moves, it looks at another sector, and then it moves, and so on. And it takes two types of data. One is it takes 2 minute, at every 2 minute it takes a picture, basically, right, of the sky. If you can analogy, so basically it takes that picture at every 2 minutes. So this is called a 2 minute cadence photos, or images, and these are for some selected targets because it cannot take these many images for the whole sky. But it also takes a 30-minute cadence full frame images, so it's a very wide region of the sky that it takes this image for. And these are the two types of data that TESS keeps on collecting. um, Moving forward, yeah, it basically looks for this dip in the brightness of the star, right? And how it does I'll explain it further. And before I move forward, like how this images are being captured, I'll just talk a bit about how TESS is, like, placed in the solar system. So this is the Earth on the right, in the middle, in the blue, and then this is the transiting exoplanet service satellite that is moving around. Over the red part, it downlinks the data to Earth and gets uplink from Earth as well. And in the blue part, in the blue region, it is looking for this the whole of the sky. So it has a 13.7 day highly elliptical, as you can see, cislunar orbit. So cislunar is basically on the other axis over here, the horizontal one. This is the moon that is orbiting Earth. So it's at an angle to this moon axis, and both are at a 2:1 resonance with the moon around the Earth. So you can see, like, two orbits of TESS would mean that one orbit of moon is complete. And it observes one sector, this 24 by 96 strip of sky that I was just talking about, at one time, dividing this whole sky into 26 regions so that it can cover most of the part of the sky. And then basically, if you calculate this, it completes observing one hemisphere in a year, and then the next year it is moving to the other hemisphere. So it was launched in 2018. It completed its primary mission in just 2 years because it covered the whole sky, like one hemisphere in one year and the other in another year. But it's still continuing, right? The mission has been extended. It is, I guess, to September of 2025, if I am up to date. But I mean, I guess Faye would be better person to answer this because I have been a bit away from this for a long time. And then you can see like this, these were the sectors that I was just talking about on the right. So these are the strips of sky, and these are 24 degrees by 96 degrees, as you can see over here. And then you can see like it is dividing the whole of sky into 26 individual sectors, or these patches of sky. And then there are these poles, right? Where you can see all the sectors are kind of submerging. So this is a region that TESS is looking at continuously. And these regions, the ecliptic poles at the top and the bottom, so north and south ones, are called the continuous viewing zones because it has an overlap with all the sectors. So it covers a time baseline of the whole year, because after 1 year it is moving to the other hemisphere. And this basically provides us an opportunity to find planets with bigger orbital period, which can be, or which might target at temperate planet candidates, which are planet candidates with having similar temperatures to Earth, maybe, right? Or we can look for habitability further on. Yeah, and I'll move on to the next part. Yep. So what we'll do now is we'll just talk about this transit detection method for exoplanets, and how does this work, right? In a coding environment, or when we are trying to actually do it by our own. What's the general way of finding these planets using the transit detection method? And this is a meme that I found on exoplanet memes for habitable planets, where transit is one of the flashy way of finding exoplanets, while the all the others are not as flashy. um, all right. So transit detection, as you can see on the right, is how a planet is moving in front of the star, and we see an apparent dip in the brightness of the star, right? So you can see, like, if I were to track the brightness of this star, I would see a dip when this planet comes in, line of sight when I'm looking at this star from my angle. So this, we basically look for these periodic momentary dips in the apparent brightness of the star, and this apparent brightness of the star is also called the flux when this planet is passing in front of the planet, front of the star. A typo here: the planet passes in front of the star. And this can be due to an exoplanet, or it can also be an astrophysical false positive, like maybe an eclipsing binary, which is a star orbiting another star, right? Or it can be an asteroid passing by, and something like that. So we are really looking for planets in this case, and not for other astrophysical false positives. And light curve is basically this graph that you're seeing on the bottom, where we are finding, or observing this brightness of the star over a period of time. So this is called a light curve, conveniently, and measuring this change in flux over time is giving us this light curve. And after we model whatever we are finding, our observations, we can find out two things with the transiting exoplanets, using the transiting method for finding exoplanets. And one is the planet radius. So basically, how deep is this trough that we are finding in the planet brightness in the light curve. This gives us an approximate, or it is directly correlated to how big the planet is, because if the planet is bigger, it will dip the brightness of the star way more than a smaller planet. And then the second one is how long this planetary transit is, or how long this brightness got dipped for. So this would tell us how what is the orbital period of this planet around the star. So these are the two main things that we find with the transiting method. And any detection pipeline, that the transit detection pipeline has these kind of steps that we undergo. So first of all, we have to download and pre-process the light curves in some way or the other. So we have light curves present at some kind of a database, which is generally the MAST database. It's Miloski Archival for Space Telescopes, I guess. That's the full form. And that's a online hosted database where you can download data from. It's free, of course. And you have to just download it in certain format. You have to pre-process it so that it's clean for you to use. The second part is detrending a light curve, which is to say that we are fitting a trend to the fluxes to remove just the variability due to stellar activity and noise. So whenever we are observing or whenever we are capturing data for a star, there might be some stellar variability, right? How the star is behaving, or there might be some noise in the data that we can remove without removing the actual transits. So this technique is called detrending the light curves by dividing the flux or by normalizing it in a way, right? So this is what we do in the first part. We retrend any stellar activity so that we are not looking at anything random. We are basically preparing the data to look for transits only. The second part is, or the third part is outlier detection and deletion. And outliers are basically, data points that occur at a very random place that you do not expect them to be, and it does not make any physical sense, right? So this can be done both pre-detrending and post-detrending. It remove outlier fluxes. So anything that is lying outside of our range of expectation. It can be due to any reason, so that you can think of. And then fourth part is the transit search itself. So we have to find some kind of periodic signal in the data, right? When we are talking about transits, it's not just a one-off transit. It will be a repeating thing. Whenever the planet is passing in front of this star, it will be dipping the brightness on a periodic way, right? And this periodism should be like a constant one. It cannot be like it is changing every time. So this finding of periodic signals in the data is called transit search. And how we do it is basically we slide a window over this data to find a periodogram. And what a periodogram means is like having continuous sets of data and finding this period. And this period is defined by the peak of this periodogram, where we are seeing the maximum correlation, or where we are seeing the maximum overlap. And last part is the transit signal identification and the follow-up. So this is kind of the confirmation part, where we are vetting if whatever we found out in our search was accurate or not, and we are checking for false positives. So there can be modeling techniques that can help us do this. And yeah, let's move to code. So Lightcurve is a package. Again, it's a free package, open source package that you can use to model, or you can search for transits using a test. So I'll just move to this. I'll just move to the part where we have these, yep, the Python notebook. So over here we have like downloading and using Lightcurve package to basically treat or download that transiting light curve and finding the planet and so on, finding this dip. And this is a very very basic tutorial, so it is using very few statements or functions from the light curve library, and using only these few functions you can basically have a light curve of your own and find out a dip in this or a transit in this. So if you do not have light curve installed, I mean run this statement, it will get it installed. I already have it installed, so I won't go into that. Then we'll use the light curve and matplotlib for plotting. Okay, I'll just import these two packages. And then once we move into this, we have a certain terminologies that we need to know before we go into it. So TIC ID is an TESS input catalog ID, which uniquely identifies each of the planet or each of the stars or the targets that TESS is looking for. Sectors we have already talked about. It is that patch of the sky that TESS is looking for at a given time. BJD is the barycentric Julian date, which is a timestamp basically that has been corrected for differences in Earth's position with respect to our solar system. So kind of an astronomical timestamp. And TBJD is measured with an offset according to TESS. So it's basically BJD minus a certain value. And then flux is the amount of light that we are receiving from the star in our image, right, or in the light curve. And then last part is normalized flux. So it's the same thing as flux, but it has just been adjusted to a common reference. So whatever the value of this light curve is, we are putting it back and compressing it to a normalized form so that it lies between 0 to 1, let's say, or 0 to 2. That can be a normalized flux. Okay, so first of all, what we'll do is light curve itself uses mass data, and it can fetch Kepler as well as test data from here. For now, we are going to identify a TIC. Like this is a confirmed planet, which was 48b. Again, a very interesting planet. You can read about it if you'd like, and we'll see what data is available for us. So I first of all imported light curve as LK. So I use this function search light curve and give it my TIC, which is the TESS input catalog ID, and then I can see I have this data that it returns to me. So it has the mission, like which mission captured this data, which year it was captured in. Then we have the author, the exp time, the target name, and the distance from Earth. So you can see what all of these mean. But for now, what we will do is we will just take out one sector of this data for this particular catalog ID, right, or this star, and we want to find out what data is present in that sector. What did TESS actually capture? So what I am doing here is I am downloading the data for the sector 1 for this light curve, and then I'm plotting this light curve. No other thing. So I'm just plotting the data that I have just downloaded from a sector for this particular star, and it looks something like this. We have some fluxes on the y-axis, and we have the time in TBJD or BTJD, same thing, on the x-axis. So we have kind of data points which are telling me how bright bright this particular star was at any given time during my this x-axis. So it's a light curve. But this might look like a very random light curve, right? There is nothing we can find out using this as it is, right? So first of all, we are going to normalize it, which involves the adjusting of light curve data so that the variations can be scaled to a relative baseline level, that is 0 to 1, for example, or 0 to 2. And this basically makes it easier for us to compare this and find a pattern. So we use this normalize function, and what it does is just normalizes, and then we just plot this normalized curve. So the x-axis is still the same, right? But the y-axis, you can see, is now normalized between 0.99 and 1.002. So it has a given set of value for us. And then we move on to manipulating this light curve. So the same things that we talked about earlier, we had to detrend it, which is also called flattening, which removes this low frequency trend from the light curve, which is supposed to be using through the stellar activity and through unnecessary noise data that we have. It uses a particular filter. You can read more about it, but it's in a very brief way, it's a filter that removes this low frequency trend from the data altogether, and it is useful for highlighting the short term variability. As I said, so stars are variable, they are not stationary. So we remove this particular we detrend the data in a way. Then for removing outliers, we can use this function remove outliers, which helps in cleaning the data by again eliminating points that deviate significantly from the rest of the distribution. So outliers like anomalies. And then remove nans. So nans are not a number values which are infinite or might be not defined, basically NA values, hash NA values, if you see on Excel or something. So these are again erroneous values that are being captured in the data, that might be captured in the data, which we need to remove. And then once we have pre-processed everything in the light curve, we fold it, which is to say we are finding this periodogram of the data, right, which is done by the fold method. And in an easier way, if you think about it, it's called a phase folding method. So if this is your data, and you can see there are these dips that you can see in the data 1, 2, and 3. What folding does is basically it stacks these individual light curve segments on top of one another, so that we can find out something like this, the end result that you are seeing in black over here. So it is basically folding on top of each other in a very simple way, and this is what helps us to find a transit, because it significantly amplifies the signal that we have. However, there are two things that are required for this. One is the period. So we need to know this window on how much of this window should be for folding. The second one should be the epoch time. So T0 is the epoch time, which is to say, like what is the highest peak in the periodogram, or in an easier way, the dip that we are seeing, or the periodicity that is originating from where. So we have this T0 and we have this period. We can fold this, and if we make mistakes over here, you can see, like if I were to select a wrong T0, it would basically shift everything onto the left. It's offsetting everything, right? The second part is if I have the wrong period, which would be more deterioratory. So basically, I have this wrong window of when the period is defined for. You'll see when I fold the things up, I'll just see some faint signals that are going down here, but it is not properly folded. So I need these two things to, find out my final goal, which is to find out the transit. And we'll just do this in a way. So I have my T0 and I have my period. This particular light curve did not needed much of, detrending and all, because it is already a very clean light curve. So we have went ahead and just put in the epoch time and the period. These two we got from the ExoFOP website, FOP website, ExoFOP, which catalogs all these stars and, catalogs all these exoplanets that have been found out, and tells us the exact epoch time and the period of this, the planetary period, orbital period of this particular exoplanet that we are talking about. So we have these two, and we'll pass these two in the fold this function called fold. And what it does is, and basically plotting it gives us this clean looking, light curve, where again on y-axis we still have the normalized flux, and then on the bottom hand we now have the phase. Again, it's in Julian dates, but it's a phase because we have folded it. It's not time anymore. All right. And the last part over here is binning. So binning in light curves or any basically time series data refers to combining data points within a specified time interval. This helps us reduce the noise and basically smooth out the data. So removing these extra points here and there, and just finding a final trend of this binned or this folded light curve. So if you can see over here, it somewhat finds a trend and gives us this final kind of the final graph that we want to have. So over here, just the same thing, we have binned it to some particular width, and you can experiment with this, put in random values, see what it does to the data and so on. And over here you can see like there is a faint yellow line, that is the bin data. That tells us, okay, this is the transit that we are looking for, without going in too much into, for each phase, it is not too much data for us. So voila, this is what we wanted. We have a transit that we can clearly see, and we can tell, okay, this is a planetary transit, and this is the end goal. And I'll share this with you. This is the same notebook that we had in Intro2Astro 2024, created by Pariti Jain. I was using the same one, but yeah, you can go through this, try it out on your own. And again, if you have any doubts, feel free to reach out. But other than that, I have just one last thing, which is the assignment for you guys. Okay, I hope my screen is, I don't think it's visible, right?
Sorry, just now. Yeah.
Yep.
Visible.
Okay, yeah, it is visible. So this is your main assignment. Just go on to exoplanet archive that we talked about in the second, session. Select any test planet, random by random, or just find out by googling an interesting planet that was detected by TESS. Use its TIC ID, the epoch and period that are already given on either the exoplanet archive or the ExoFOP website, and then plot this transit light curve for that planet. Should be different from this one, of course, but anything works. And just look at it and submit the assignment. And then the bonus assignment is basically you can use box least square method to find out this epoch and the period as well. So this is a method that is used to search for planets. Right now we are already giving it the period and epoch, but for a new planet, when we are finding a new planet, this is something we have to find out ourselves. So try out the box least square methods. I have put on a link over here that you can head on to and learn about it. And then you'll be able to, find out the period and epoch yourself, so that you can find the final goal, which is a new planet. So do this for any existing planet and find out how close you are with the real values. If you are going fine, you can replicate it to any random data and see if there is a exoplanet over there or not. But yeah, this is all. Thank you so much for your attention. And if you have any questions, feel free to reach out on Discord or reach out to me on my email. I'll try to answer as much as possible. I have not been following up on a lot of questions, but I'll do this week.